Welcome to Financial Statistics. Today we are going to explore one of the most fundamental concepts in finance, the difference between deterministic and random cash flows. Imagine lending money to a friend versus investing in a brand new startup. One offers a guaranteed return, while the other is a gamble. Understanding how to mathematically value both of these situations is the absolute foundation of pricing assets, managing risk, and making smart financial decisions. Let us dive in and see how we can put a concrete price tag on the future. To begin, let us look at deterministic cash flows. Imagine you lend money to a highly trusted friend and they promise to pay you exactly $100 every month for a year. You know exactly how much money is coming in and exactly when it will arrive. In the financial world, this is called a deterministic cash flow. When we say it is deterministic, we mean that the future amounts and their exact timings are known with absolute certainty today. You do not need to worry about the economy or business performance. A classic example is a government bond, where the government promises specific interest amounts on unchangeable dates. Now that we understand what a deterministic cash flow is, we face a new challenge. Because we know exactly what we will receive in the future, our main task is figuring out what those future payments are worth to us right now, today. This brings us to the concept of present value. We must calculate this because of the time value of money, which is the universal rule that a dollar today is worth more than a dollar tomorrow. Why? Because you could invest today's dollar and earn interest on it. To find the present value, we use a mathematical process called discounting, which shrinks future amounts back to their equivalent value today. This concept of discounting leads us directly to our first formula. Suppose you invest an amount today at a certain interest rate for 1 year. To find what you need to invest today to get a specific future amount, we rearrange the growth equation by dividing by the growth factor. Here, PV stands for present value. CF1 represents the cash flow received at the end of year 1. The symbol R is the discount rate, representing your opportunity cost or the return you could have earned elsewhere. If the discount rate increases, the denominator becomes larger, which means the present value decreases. This makes perfect sense. If you can earn a higher interest rate elsewhere, a fixed future payment is less attractive to you today. Building on that single period formula, what happens if we have multiple payments over several years? We simply discount each payment by the number of years we have to wait for it, and then add them all together. The mathematical symbol for adding them all together is the Greek letter sigma. The variable t represents the specific time period when the cash flow occurs, starting from year 1 up to the final year n. The denominator grows larger as t increases, meaning that cash flows received further in the future are shrunk or discounted much more heavily than cash flows received soon. For deterministic cash flows, we usually look at current risk-free interest rates, like treasury bills, to find our discount rate. Before we move on, let us see this with a concrete example. Suppose a highly reliable bank promises to pay you $100 exactly 1 year from today and another $100 exactly 2 years from today. The current risk-free interest rate is 5% per year. We want to find out exactly how much this series of guaranteed payments is worth to you today. We will use the present value formula for multiple periods. We set up the equation to handle the year 1 payment and the year 2 payment individually. Then we substitute our known values into the equation using 100 for the cash flows and 0.05 for the interest rate. Continuing with our calculation, we now calculate the denominators. Notice how the denominator for year 2, which is 1.1025, is larger than the denominator for year 1, which is 1.05. This mathematically proves that you are penalizing the second payment more because you have to wait longer to receive it. Next, we perform the division. The $100 you get in year 1 is worth $95.24 today. The $100 you get in year 2 value is worth only $90.70 today. Finally, we complete the process by adding these two discounted values together. We find that total present value is $185.94. This means that receiving those two future $100 payments is financially identical to having exactly $185.94 in your hand right now, assuming you could invest it at a 5% interest rate. You have successfully priced a deterministic cash flow. Now let us step into the real world, which is rarely perfectly predictable. Imagine you open a small coffee shop. You hope to make $500 next month, but you cannot be certain. If the weather is great, you might make $800. If a storm hits, you might only make $200. This is a random cash flow. A random cash flow is a future payment whose exact amount is uncertain today. Instead of a single guaranteed number, you have a range of possible outcomes, each with a certain chance of happening. Almost all investments in the stock market, real estate, and private business involve random cash flows because the future is full of surprises. Because we are dealing with uncertainty, we need a new mathematical tool. In financial statistics, we model random cash flows using probability distributions. A probability distribution is simply a mathematical list of all the possible future cash flow amounts paired with the exact percentage chance that each amount will actually occur. Because we do not know which specific outcome will happen, we rely on a crucial concept called the expected value. The expected value is the weighted average of all possible outcomes. It tells us what we would earn on average if we could repeat this exact same uncertain investment thousands of times. Remember, the expected cash flow is our mathematical guess made today, while the realized cash flow is the actual hard cash we end up receiving. To calculate this expected value, we take every possible future cash flow amount, multiply it by its probability of happening, and then add all those pieces together. Let us look at the formula. ECF is the expected cash flow. The variable I represents a specific possible scenario, like good weather or bad weather. CFI is the cash flow amount that will happen if scenario I occurs. The term PI is the probability, written as a decimal between 0 and 1 that the scenario will actually happen. The sigma symbol tells us to sum up these probability-weighted amounts for all n possible scenarios. If the probability of a very bad outcome increases, the overall expected value will decrease. Let us apply this formula to a real-world investment decision. You are considering investing in a startup company for 1 year. After analyzing the market, you determine there are 3 possible outcomes. There is a 20% chance the startup fails and pays you $0. There is a 50% chance it does okay and pays you $100. There is a 30% chance it becomes a massive hit and pays you $400. We expand the summation formula for our 3 specific scenarios: failure, average success, and massive success. Then we substitute the given probabilities as decimals and the cash flow amounts into our equation. Now we perform the multiplication for each scenario. The failure scenario contributes $0 to our expectation. The average scenario contributes $50. The massive success scenario contributes $120. By adding these together, we find the expected value is $170. This means that mathematically, the uncertain future payoff is valued at $170 today. However, remember the difference between expected and realized. When the year ends, you will receive exactly $0, $100, or $400. You will never actually receive exactly $170. It is just the probability-weighted average used to help you decide if the investment is worth buying today. To solidify these concepts, let us look at them side by side. On the top, you see the deterministic cash flow, represented as a straight, predictable timeline. At year 1 and year 2, there are solid arrows pointing to exactly $100. There are no branches because there are no alternative possibilities. On the bottom, you see the random cash flow, represented as a probability tree. From year 0, the future splits into 3 distinct branches. Each branch represents a different state of the world, labeled with its probability and its specific cash flow outcome. This visual perfectly captures the difference between a guaranteed path and an uncertain future. Now that we have visualized the difference, why is this distinction so critical? Understanding the difference between deterministic and random cash flows is the absolute foundation of all financial valuation. If you cannot distinguish between a guaranteed payment and a risky guess, you will inevitably price assets incorrectly and lose money. Deterministic cash flows are used to price safe assets, like government bonds, allowing the global credit system to function smoothly. Random cash flows are the basis for pricing stocks and complex derivatives. In the real world, investors demand a higher return, meaning a higher discount rate, when facing random cash flows to compensate them for the anxiety of uncertainty. This extra return is known as the risk premium. We have covered a lot of ground today, so let us review the key takeaways. First, deterministic cash flows are guaranteed future payments, where both timing and amount are known with absolute certainty. Second, we value these guaranteed payments using standard present value discounting, shrinking future dollars to their worth today. Third, random cash flows are uncertain future payments that we must model using probabilities. And finally, we evaluate these uncertain flows by calculating an expected value, which is the probability weighted average of all possible outcomes. Mastering both of these concepts allows you to navigate both the safe and the risky sides of financial markets with mathematical confidence. Great job today.